Have you ever wondered how the universe began? Today we dive into the Big Bang Theory, the leading explanation about our cosmic origins. Imagine stepping back in time, over 13 billion years, to witness the very inception of everything we know. The Big Bang Theory isn't just a popular idea, it's the cornerstone of modern cosmology, embraced by the global scientific community. This theory paints a picture of the universe emerging from an infinitely small, hot, and dense point, often referred to as a singularity. But why do scientists gravitate towards this theory? It's because the Big Bang provides a compelling explanation for a variety of phenomena. From the expansion of the universe to the distribution of distant galaxies and the existence of cosmic microwave background radiation, the Big Bang Theory helps us connect the cosmic dots. It's a narrative that begins not with a whimper, but with a spectacular and profound explosion. Keep watching as we break down this fascinating theory into its core components. What existed before the Big Bang? This question teases the edges of human understanding and cosmic mystery. Before the monumental event that sparked the universe, there was no before because time itself didn't exist. Picture, if you will, a state of absolute nothingness, not a vacuum or empty space, but a singularity. This isn't nothing as we might think of it, but rather everything, the entire mass and energy of what would become the universe, compressed into an infinitesimally small point. In this singularity, the laws of physics as we know them cease to operate. Space and time are intertwined, and as such, the concept of before becomes meaningless. This singularity is not just a small dot floating in a pre-existing space, it is all of space. Every particle, every bit of energy, compacted into one dense point, devoid of time and dimension. With this singularity in place, the stage was set for a colossal event. Imagine all the universe's energy bursting from a single point. This vivid imagery takes us to the very heart of the Big Bang Theory, where an inconceivably dense and hot state marked the inception of everything we know. In the depths of this primordial moment, the universe was not as we see it today. Instead, it was condensed into a single point, smaller than a grain of sand, yet containing all matter, all energy, destined to become everything that exists today. From this tiny, dense state, the universe began its first major transformation. The Big Bang wasn't an explosion in the traditional sense. There was no shattering sound or fiery blast as one might imagine. Rather, it was an expansion, an event that saw the universe stretching itself out from that infinitely small point. Within a fraction of a second, a phenomenon known as cosmic inflation took over. This was not merely expansion. It was an exponential surge that stretched the fabric of the universe faster than the speed of light. During these first moments, the universe doubled in size countless times in less than a blink of an eye. It's a concept that challenges the very limits of human imagination, the entire cosmos multiplying in size within the confines of a cosmic instant. As this dramatic expansion unfolded, the universe cooled rapidly. The energy that was once unimaginably condensed began to transform. From pure energy came quarks, and shortly thereafter, protons and neutrons. These particles eventually led to the formation of hydrogen and helium, the fundamental elements that would go on to fuel stars and forge the complex array of elements we find in the periodic table today. This explosive expansion created the vast cosmos we are part of today. From that singular dense point, a universe of boundless scale and beauty unfurled, setting the stage for everything from galaxies to planets, from stars to life itself. In the grand tapestry of the cosmos, the Big Bang serves as the most explosive and prolific beginning imaginable. Following the big explosion, how did the first elements form? Let's dive into the fascinating sequence of events that took place in the early universe. After the Big Bang, the universe was an incredibly hot, dense state. As it expanded, it began to cool down gradually. This cooling phase was crucial for the formation of the first elements. Within the first few minutes of the universe's existence, temperatures dropped to the point where protons and neutrons could combine to form nuclei, a process known as nucleosynthesis. Initially, the simplest elements, hydrogen and helium, started to take shape. Hydrogen, the most abundant element in the universe, formed from single protons. Helium, on the other hand, came from the fusion of protons and neutrons. These processes were incredibly rapid and efficient, occurring within the first 3 to 20 minutes after the Big Bang. As the universe continued to cool and expand, the intensity of these reactions decreased and the formation of new elements slowed down. The majority of the universe's mass remained hydrogen and helium, with trace amounts of lithium and beryllium. Later, as gravity pulled hydrogen and helium gases together, they formed stars. Inside these stars, the process of nuclear fusion reignited. Stars became cosmic forges, where hydrogen atoms fused under extreme pressure and temperature to form helium, and heavier elements were created from helium atoms fusing together. This stellar alchemy filled the universe with a rich variety of elements, which are essential for everything from the air we breathe to the planets we inhabit. These elements are the building blocks of everything in the visible universe. What evidence do we have for such an explosive beginning? Well, one compelling piece of evidence lies in the cosmic microwave background radiation, or CMB. This is essentially the afterglow of the universe's dramatic birth, the Big Bang. The CMB is a fascinating phenomenon. Imagine the universe about 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that it was essentially a plasma soup, where photons or light particles couldn't travel freely. They were constantly being absorbed and re-emitted by charged particles. But as the universe expanded, it cooled down. Eventually, it reached a temperature where atoms could form, allowing photons to travel freely. This moment is known as the recombination. The photons released during recombination have been journeying through space ever since, stretching and cooling as the universe itself expands. Today, these photons appear as a faint glow permeating the entire cosmos, observable as microwave radiation. This is the CMB. Astonishingly, the CMB is incredibly uniform in temperature, only varying by 1 part in 100,000. These tiny temperature variations are crucial. They indicate regions of slightly different densities in the early universe, which would later evolve into the galaxies and cosmic structures we observe today. This cosmic relic radiation provides a snapshot of the infant universe, offering clues to its earliest moments. How do we know the universe is still expanding? This question has intrigued astronomers and cosmologists for decades, and the answer lies in the behavior of galaxies far beyond our own Milky Way. First, let's talk about the redshift of galaxies. When we observe the light emitted by galaxies, we notice something fascinating. The light is shifted towards the red end of the spectrum. This phenomenon, known as redshift, occurs because the wavelengths of light stretch as they travel across the expanding space of the universe. Think of it like the sound of a receding train whistle changing pitch due to the Doppler effect, but with light. Speaking of the Doppler effect, it's a concept you might be familiar with from everyday experiences, like hearing the pitch of a siren change as an ambulance drives past. In the cosmic scale, the Doppler effect helps us understand how galaxies are moving in relation to us. If a galaxy is moving away, its light waves stretch, making them appear redder. Conversely, if a galaxy is moving towards us, the light waves compress and appear bluer. The predominant redshift in distant galaxies suggests they are moving away from us, and indeed, from each other. This brings us to the groundbreaking work of Edwin Hubble in the early 20th century. Hubble observed that not only are galaxies exhibiting redshift, but the farther a galaxy is from us, the faster it appears to be moving away. This relationship, now known as Hubble's law, was revolutionary. It implied that the universe itself is expanding, and that it was once far smaller, hotter, and denser than it is today. Hubble's observations laid the foundational evidence for the Big Bang theory. They suggested that the universe had a definite beginning and has been expanding ever since. Today, measurements of cosmic microwave background radiation and the distribution of galaxies continue to support this model. The expansion of the universe continues to be a critical piece of evidence for the Big Bang theory. So why does the Big Bang theory matter to us? This question brings us to the heart of our cosmic curiosity. The Big Bang theory isn't just a story about the past, it's the foundation of our understanding of the universe. It tells us that about 13.8 billion years ago, the universe started as an infinitely small point and has been expanding ever since. This grand expansion laid down the cosmic framework within which galaxies, stars, and eventually planets formed. By studying the Big Bang, scientists have been able to piece together a coherent narrative of the universe's history. This theory helps us understand the formation of all matter, the laws of physics as they are known today, and the initial conditions that led to the universe's current state. It's a vital part of astronomy and physics, influencing everything from the way we perceive time and space to advancements in technology that rely on our understanding of these fundamental concepts. Through understanding the Big Bang, we glimpse the universe's birth and our extraordinary cosmic journey,